Yeah.
And I was working on it. So.
Thank God, the only two homeworks that I do construction was narrow. The fact that Harold was just like 8x5.
Oh.
8x5.
I did that like last Wednesday.
Oh, nice.
It's been sitting in the OneDrive.
I didn't do it until
there,
last
Paul?
night at 7 p.m. I'm like,
Hello, check,
it
check.
wasn't bad. It was just kind of like,
Say
oh, time to go to
something.
sleep now that I do it on this. Oh, wait, V1? V1?
These notes are so good. They're fun. They're in the notes.
They're in the notes. Last problem. That one I know. Really? I don't know, the first one should be like 5. 6? Okay. Oh, yeah, always. But, yeah, no, like this week it's like one computational kind of problem where you're doing, I think, curl B.
That's the first one.
That's the first one, and the rest of them is just derivations. Which one?
Okay, one person online. Can you hear me? Say something. Check, check, check. Say something. Paul? Hello? Are you there? Hello? Hello? Well, he's gonna log back in if he wants to. Oh, okay. Can you hear me? Check, check.
Yes, I can hear you. Sorry about that.
No problem. Got it. Anybody else online? No, just one person. Okay, so I'm going to mute you. Yeah, please unmute your microphone anytime.
Friday, Saturday.
Oh shit.
They're not bad. It's just, they take hours because they're like 25 problems.
They take both of them would take me around an hour.
Hour and a half.
Okay, well, the last one I got like 70% on because I just went in and I was like,
It's only 5% of my grade.
yeah, no. I just went through the whole thing. And like, that seems right. That seems
Well,
right.
our time doesn't need 24 hours.
Yes, for like 6 of them.
But
One of my, or actually my students, and I
Thanks to Curiosity Stream for sponsor.
do a bunch about this class because we just help each other.
yeah.
But for one of the quizzes, it was that weekend when the internet went out.
Yeah.
So it automatically saved, and when you submitted it, it took like 17 hours to complete.
Oh.
Because the timer kept running the entire time.
Okay, everyone. So let's just begin today. Taking in-class attendance. Here we go. Thank you. Maybe I should take
Vomiting force.
Most people No, it's not.
Well, that's more dragon. This is just,
Chicken drumstick.
artistic. I think I need to put some stripes on it.
I'm not going to ask, right? How much you want to start with if you haven't already announced it? Because I've had classes since like, how much you want to
What?
If you haven't already announced it, I haven't changed my Outlook email because I have classes since 8 in the morning. So unless he's already announced it, and I wouldn't know. But how much you want to that quiz Monday?
Okay, so let's begin today.
I hope it's not.
I hope it's not, but I'm like, maybe Wednesday. I hope it's not.
So there's no new update. So I hope you are working on homework of Unit B1, which is this Friday. Those may not necessarily be easy homework assignment. Okay, so you start early. If you have any question, please ask me. Okay, please do not assume that you can do it on Friday night. Oh, actually, Friday night is late. Thursday night. Friday night. Too bad.
As long as he doesn't take away that OneDrive folder, we're good.
Well, 1.4 days all gone. How can I submit? Well, you have to literally start begging. Oh, professor, I forgot. Could you please still take it?
That's when
And
your
then
forehead
professor
touches
goes
the
like,
floor.
Tell me. Any question about homework?
Dr. H, I was
Okay.
trained.
Unit B1 is all about mathematics, but it's quite important foundations of Unit B2, B3, B4. Okay, and then obviously what's next to come? Project phase 2A and B comes up right after Unit B3. Okay, it is essentially circulation theory of aerodynamics, today's subject. Circulation of a flow field. Okay, so let me introduce the whole discussion of this most important concept of this aerodynamics class. The meaning of you taking aerodynamics class is to understand circulation theory of aerodynamics. It is the theory of aerodynamics, which is a classic theory based on Prandtl's circulation theory. German origin. Okay. Now, it is quite important. You have to understand this is not 100% established theory yet. People still debate on it, okay? So here is interestingly, no one really understands why airplane flies. And then I bumped into one of the professors of aeronautical science department, Professor Sean Gerald. Do you know him? Yeah, we have always kind of joke each other. He teaches aerodynamics for pilots. I teach aerodynamics for engineers. We kind of back to back in the same class oftentimes. So when I kind of about ready to leave my classroom, he comes in and look at the equations on the whiteboard and he says, he laughs at it. Oh, you guys work on equations, huh? You guys know how to fly airplanes. And then, well, bottom line, no one knows why airplane flies. And he said, well, we know how to fly airplane. Well, that's not the same meaning, okay? If you guys know how to fly airplane, that is always reactive. That means if that's the only thing you know, how do you design airplane and make it better? This is only one way. You build something, test it. If it crashes, modify a little bit, test it, crash again, modify a little bit, test it, crash again, somebody die, modify it. That's the only way. That's the only way you can design airplane, right? I'm not kidding. That's pretty old Russian 1950s MiG-21. How many versions do they have? I don't know.
Way too many.
Modify it, crash it, modify it, crash it, somebody died, modify it, crash it. Okay, so we really want to know why. That is the aerodynamics theory, our attempt to understand why airplane generates the lift. So why is most important, and then let's take a look at the video today to begin with, okay? This is some kind of entertainment video, but I thought it was quite interesting. So it's about 10 minutes. This is going to set the foundation of a whole discussion, okay? Here we go.
Thanks to CuriosityStream for sponsoring this video. Since well before the first Wright brothers flight in 1903, and all the way to the present day, mankind has been fascinated by taking to the skies. Once thought to be impossible, heavier-than-air flight is only a reality because of the lift generated by aircraft wings. But lift is a complicated topic, and even to this day, engineers have lengthy debates about how it's created. So what exactly is lift? When fluid flows past an object, or an object like this plane wing moves through a stationary fluid, the fluid exerts a force on the object, which can be split into a component acting in the same direction as the fluid flow, called drag, and a component acting perpendicular to the flow direction, called lift. When talking about lift, we're mostly interested in streamlined bodies like this airfoil, which are carefully designed to produce a lot of lift, but to minimize drag. Lift-producing airfoils can obviously be found in airplane wings, but also in many other applications, like wind turbine blades, or propeller blades. They're also used in the wings of Formula One cars, which are designed to generate downforce so that corners can be taken at higher speeds. Airfoils come in a huge range of shapes and sizes. One designed for an aircraft wing won't be optimized for a propeller blade, for example. And a wing designed to fly at supersonic speeds will have a very different profile compared to one designed to fly slower than the speed of sound. Airfoil profiles can be defined using a few different parameters. The forwardmost edge of the airfoil is called the leading edge, and the trailing edge is at the back of the airfoil. Drawing a straight line between the leading and trailing edges gives us the chord line. The angle between the chord line and the flow direction is called the angle of attack. Drawing a line which is midway between the upper and lower surfaces gives us the mean camber line. Camber describes how curved an airfoil is. We can have positive camber or negative camber, and a symmetrical airfoil has zero camber. Camber and the angle of attack are important parameters that will have a large influence on how much lift an airfoil can generate. So how does a humble teardrop shape generate enough force to lift heavy aircraft off the ground? As the fluid flows around the airfoil, it creates two different types of stress which act on its surface. First, we have the wall shear stresses. These stresses act tangential to the object's surface and are caused by the frictional forces that act on the airfoil because of the fluid's viscosity. Then we have the pressure stresses. They act perpendicular to the object's surface and are caused by how pressure is distributed around it. Lift is the resultant of these two stresses in the direction perpendicular to the flow. The only way a fluid can impart a force onto an object is through these stresses. Integrating the stresses in the lift direction over the surface of the airfoil gives us the lift force. For streamlined bodies like airfoils, the shear stresses will mostly be acting in the same direction as the flow. They will make a large contribution to the drag force, but won't contribute a significant amount to the lift force. And so we can neglect them and say that the lift acting on an airfoil is caused by the way pressure is distributed around it. A typical pressure distribution looks something like this. The pressure is low above the airfoil and high below it, which creates a net force with a large component in the lift direction. If we plot the pressure profile along the top and bottom surfaces, we can see that the low pressure on the top surface is larger in magnitude than the high pressure on the bottom surface. So the suction pressure on the top surface is what contributes most to the total lift force. We can also see that the majority of the pressure difference is coming from the forwardmost part of the airfoil. In truth, there's nothing particularly special about the shape of an airfoil that allows it to generate lift. Any object that creates an uneven pressure distribution will generate a force in the lift direction, like a flat plate at an angle relative to the flow, for example. Airfoils are just optimized shapes that have been carefully designed to have high lift-to-drag ratios. Without a difference in pressure above and below an object, there can be no lift. A symmetrical body, like this bullet, doesn't generate any lift force because there's no pressure difference around it. So we know that lift is caused by the pressure distribution around the airfoil. But where does the pressure distribution come from? The answer to this question is complex, and there's much debate about the best way to explain it in a concise way. We can broadly split the different explanations into two groups, those based on Bernoulli's principle and those based on Newton's third law. Bernoulli's principle explanations focus on the velocity of the fluid. If we look at how fluid flows around the airfoil, we can see that close to the leading edge, there's a point where the fluid velocity is reduced to zero. This is called the stagnation point. Outside of the thin boundary layer surrounding the airfoil, the fluid flowing above the stagnation point over the top surface of the airfoil travels faster than the fluid traveling over the bottom surface, as we can see from these particles. Bernoulli's principle tells us that when the velocity of a fluid increases, its pressure must be reduced, which is just a statement of the conservation of energy. This means that the increase in velocity above the airfoil creates an area of lower pressure, and the reduction in velocity below it creates an area of higher pressure, and this pressure difference creates the lift force. But then, we need to explain what causes the difference in velocity. One explanation is that the geometry of an airfoil causes the flow to be pinched together above the airfoil, but not below it. Because of the conservation of mass, this results in increased velocity above the airfoil. A more complete but less intuitive explanation for the difference in velocity is based on the concept of circulation. The flow around an airfoil can be thought of as the superposition of idealized uniform irrotational flow and circulatory flow. Without circulation, the flow around the airfoil would look like this. This is clearly non-physical, since the fluid can't turn such a sharp corner at the trailing edge, and so the airfoil must be generating some circulation. If we impose a condition that says the flow above and below the airfoil must be parallel when leaving the trailing edge, we can calculate the exact amount of circulation that must be generated by the airfoil to do this. This is called the Kutta condition. Circulation has the effect of accelerating the flow above the airfoil and delaying the flow below it, which gives us the explanation we need so that we can apply Bernoulli's principle. What about the explanations of lift that are based on Newton's third law? These don't consider the velocity above and below the airfoil, but instead look more generally at the behavior of the fluid. If we look at a wider area, we can observe that the effect of an airfoil can be felt far beyond its immediate vicinity. Upstream of the airfoil, the flow is being swept upwards, which is called upwash, and downstream the flow is deflected downwards, which is called downwash. A very large volume of air is being displaced by the airfoil. Newton's third law tells us that for every action there is an equal and opposite reaction. The airfoil must be imparting a force on the air to create the downwash, and so based on Newton's third law, there must be a corresponding reaction force acting on the airfoil. In other words, an airfoil generates lift by turning the incoming air downwards. We can use the concept of circulation again, this time to explain how the upwash and downwash are created. In summary, a lift force acts on an airfoil because of the pressure distribution around it. The exact cause of this pressure distribution is complex and can be explained in several different ways, which approach the problem from different angles. Explanations based on Bernoulli's principle and on Newton's third law provide valuable insight into how lift is generated, although both approaches have limitations, partly because they're based on cause and effect relationships. The problem is that there isn't always a clear cause and effect relationship between the different phenomena which are involved in generating lift. Whether we're talking about the fluid velocity, the pressure distribution around the airfoil, or the downturning of the fluid. In reality, all of these things are happening simultaneously and are mutually interacting. Nevertheless, these explanations are useful and can lead to a more intuitive understanding of lift. We can easily imagine, for example, that increasing the camber of an airfoil will allow it to deflect a larger amount of fluid, and so will increase the lift force. The same is true for the angle of attack. Increasing the angle of attack deflects more fluid and increases lift. However, there are limits to this logic. Once the angle of attack reaches a certain critical value, we can observe a sudden decrease in the lift force. For this airfoil, it occurs at around 16 degrees. At this angle of attack, the boundary layer is no longer able to remain attached to the airfoil, and it detaches from the surface, creating a wake behind it which affects the pressure distribution around the airfoil, significantly reducing lift and increasing drag. I covered flow separation in detail in my video on aerodynamic drag. The sudden reduction in lift is called stalling, and it can be very dangerous for aircraft. Different airfoil shapes can have drastically different lift characteristics. This airfoil is cambered. If an airfoil is symmetrical, and so has zero camber, the lift force will be 0 for 0 angle of attack. Aerobatic aircraft usually use symmetrical airfoils since they allow planes to fly upside down more easily. Lift is generated by lifting the nose of the plane to create an angle of attack. Modern aircraft wings are equipped with flaps and slats, which allow the shape of the airfoil to be adjusted and optimized for different phases of flight. During takeoff, for example, you want high lift. Extending the flaps increases the camber of the wing, which increases lift, and so flaps are extended during takeoff. But the extra lift comes at the expense of increased drag, and so the flaps are retracted when cruising, since high lift is no longer needed, and drag should be minimized to improve fuel consumption. This video has really only scratched the surface when it comes to developing a complete understanding of lift. If you'd like to dive a little deeper, you can start by checking out the extended version of this video over on Nebula, where I've covered some more advanced aspects, like how circulation is induced, and how the Kutta-Joukowski theorem can be used to calculate the lift force. Nebula is a streaming platform built by...
Yeah, okay. So, yeah, we're gonna cover that. Voltage shading at the startup and also current condition, all of those mathematical details that this video actually started to kind of discuss about. So this actually covers some foundation. We are going to get into a little bit more details in mathematical sense. So knowing the basic foundational discussion is actually better to understand deeper later as you go into math. Question, go ahead.
Yeah, for the slats, do they move?
They move over.
Eh?
Slats.
The
Slats. Slats, yeah. It just creates a gap here. It's a leading edge device. It's called slats. We're gonna cover that. Don't worry about it. Just to stay tuned. Okay. All right. So somebody actually joined in the middle. I forgot to make my status. Don't disturb. Yeah, sorry. Okay. So we are going to actually start talking about circulation. So circulation came up in the video, right? So circulation is essentially you are going to have a tendency of changing the direction of the incoming uniform flow because of the presence of your body. This body is typically called airfoil, cross-section of the wing, and also typically comes with angle of attack. So those two combinations actually have a circulation introduced in the flow field. That circulation is going to create the lift. Okay? So there is an interesting, very important equation in aerodynamics. It's probably the most important equation of aerodynamics. Occasionally, most important things in each class comes in very simple format. What's the most important equation of dynamics? Everything. That's a very simple equation. Is everything in dynamics. Now in aerodynamics, it's called Kutta-Joukowski theorem. That's the most important equation of aerodynamics. That actually relates the circulation to the lift. But anyway, circulation that the video was talking about, the circulation can be computed mathematically. This is called circulation. Okay. So circulation can be computed just like that, either line integral or area integral of what's that?
Curl B.
Del cross B, what you call that?
Gradient.
This is called vorticity, right? Gradient or curl of velocity field. So suppose if the velocity field information is all given, you're going to mathematically take the curl of a velocity field. It's called the vorticity. We know that. Do you remember last class? Yeah. Vorticity. What's this? This is vorticity. Here we go. All right, this is vorticity. Del cross B, curl B. Okay? So this is essentially the information you can get from the flow field, which is velocity field, essentially. Okay? If the velocity field information is given mathematically, complete description is given, you can determine the vorticity. Once you know the vorticity, you can determine the circulation. However, we want to avoid that kind of discussion, right? Because vorticity can be 0. It's called what? If the vorticity is zero, what do you call that flow field?
Irrotational.
It's called irrotational flow field. So we want to simplify this equation, assuming that the flow field is irrotational. In other words, we are going to completely ignore the viscosity. It's called ideal flow field. So if the ideal flow field is concerned, circulation of the flow field can only be given by the line integral. Okay? Not the area integral, because vorticity is zero. If the vorticity is zero, if you try to integrate zero over the area ds, what do you get?
Zero.
Not the zero. Some kind of constant we cannot determine. It's indeterminate. If you integrate zero, that is indeterminate. You need extra information to determine that constant. That constant could be zero, but we never know. Indeterminate integral here, if it's irrotational flow field. So we're going to usually do mathematics of line integral, velocity dot product ds line integral. Okay? So this is going to determine circulation of a flow field. Once you determine the circulation, by the way, are you doing the homework of Unit B1? And have you ever seen this kind of homework assignment? Like a line integral versus area integral, and then Stokes' theorem says it's equal to each other. Have you done that? Homework of Unit B1, which is due Friday. Are you doing it? Have you seen this kind of math? Those two must be equal to each other. Why? Because of what? Stokes' theorem, yes. Are you working on home in a timely manner? Or do you plan to wait until Thursday night? It's going to make your life different. Of course. One is engineering, one is non-engineering. Okay? So again, it's important. Stay tuned. Okay? So I'm forcing you to do both of mathematical manipulation in homework of Unit B1. You have to do it. You know how to do it. Okay? So once you do it, without knowing what you're trying to find, you're trying to find out the saturation in homework of Unit B1. You probably don't know what you're doing. Oh, this is a homework Dr. H forcing me to do. Now you realize, hey, I'm computing saturation in the flow field. Yeah, that's right. That's what you do. Okay? So knowing that you can compute the saturation of the flow field mathematically, what is the next step? Next step is Kutta-Joukowski theorem. In other words, Kutta-Joukowski theorem, based on the saturation you compute in the flow field, you can determine lift. Next page. This is Kutta-Joukowski theorem. Very simple equation. Surprising, eh? And this is lift can be generated if you know the saturation of the flow field. So this is lift per unit span. How much lift you can generate per unit span of a cross section of a wing called airfoil is equal to density times V infinity uniform flow multiplied by saturation. Those two combined together is going to be a flow field with a lift. This is called Kutta-Joukowski theorem. Very simple theorem. Most important equation of aerodynamics, in which you've seen in the video, right? Okay. This is called classic circulation theory of Crandall, German origin. The theory of aerodynamics of this country. Okay. So we are going to actually combine Bernoulli's principle plus Newton's third of motion interchangeably almost always, trying to explain how the circulation is generating lift. Okay, that is what the software is all about. X25. This software uses that theory. Okay, this is circulation theory of aerodynamics. So this actually hopefully gives you why airplane generates the lift. Knowing why is important. Otherwise, unless you know why, you can never predict anything new. It's not that the airplane pilot says, well, we know how to fly airplane. Well, that doesn't mean you can design and modify and make it better. Because you can only do reactive thing, trial and errors. That's not the design at all. Okay, so you're talking about airplane design, you're going to analyze it based on the theory. That means you need to understand every single detail of aerodynamic theory. Otherwise, you are not qualified to be an airplane designer. Okay, you can be a worker, but you cannot be an airplane designer. It's going to be two different kind of job categories. So please, I hope, as long as you're taking my aerodynamics, please understand everything. that I'm going to cover. So this is going to be based on theory of aerodynamics, circulation theory. Okay? So this X55 was developed based on Xpoil. Xpoil is a software which is developed by a professor at MIT, Professor Mark Doretta. And then later on, a group of people actually combined this Xpoil in a batch processing so that this software actually runs cities of Xpoil in different conditions, different Reynolds number, different angle of attack, and batch processing lots of data sets, creating a database of 2D cross-sections behavior, and then use that to design your wing. So your wing is created by this section, that section, that section. Could be 3 different shapes, could be 3 different angle of attack and angle of incidence. It could be lots of modification you can do. Okay? But as long as you know the behavior of each cross section, it is essentially integration from tip to tip. That's your wing 3D behavior. You can predict only through the software. You can never do it by hand. So before this software was introduced, senior design project of aerodynamics person's job is essentially trial and error. That's the only thing you do. Nowadays, you can analyze and present your analysis, and then based on your analysis, you can optimize your wing shape. Okay. If I were to teach senior design capstone, at least I want to see that kind of analysis. If that kind of analysis is not done, I'm not going to call that airplane design so that seniors, you cannot graduate. That's what I would say. Now, I'm not teaching senior design, so I don't know what other people say. But anyways, let's take a look at example here. Try to find out circulation of this very simple flow field. Okay? This is just a demonstration of how mathematically you can determine circulation of a flow field. Now, this is going to be a precursor to your project 2A and 2B. You are going to deal with the flow over circular cross-section. Okay? Flow over circular cylinder. That's your project upcoming. So this is sort of like an introduction demo of how to handle mathematics and flow over circular cylinder. Obviously, what kind of coordinate is better to handle this kind of mass? Polar coordinate. Here we go. So we are going to actually use the polar coordinate to do a line integral to determine circulation of this flow field. Okay. Now, whoa, is this a polar coordinate velocity? Wait a minute. Velocity is given in some kind of coordinate. What's this? This is Cartesian x and y coordinate based velocity profile. Do you want to integrate as is? No. Oh, do you want to do this? How? I mean, you can possibly do it using MATLAB. You can do it, but using by hand, do you think you can do it? So first question is, what kind of velocity field? This is actually, I'm going to give you like a, oh, okay. I created this program based on the knowledge I know. This is irrotational flow field. This is irrotational flow field. That means if you take mathematical operation del cross B, it is going to show you this is a 0. So this is curl of velocity field. If you do it in 2D Cartesian coordinate system, you're going to receive the 0 result. So this is irrotational flow field, something called point vortex flow. Okay. Point vortex flow. You are going to be given point vortex flow analysis later on in Unit B3. So this is just a preview of what's going to happen in Unit B3. Point vortex. Interesting, okay? Don't be fooled by words. This is a vortex flow field. What kind of flow field? This kind of flow field. Vortex flow field. Do you have a vorticity on it? vorticity is 0. This is a vortex without vorticity. Then you go like, huh? This is a vortex without vorticity, irrotational vortex. Okay. Do you think this has a circulation? Yeah. How do you create the circulation? Circulation is there because this is this kind of flow field. However, this is irrotational. That means this is the originally cubic element. As it moves around the circular motion, it doesn't rotate in their form. So this is irrotational vortex without vorticity, but it has a circulation. Is it confusing enough? You can talk to your parents like this. Do you know this is a point vortex without vorticity, but there's a circulation, okay? Then you go, oh, it makes a perfect sense. Yes, that's right. So let's just find out circulation. Knowing that there's no vorticity, this is irrotational vortex.
So
It's called point vortex. Go ahead.
So the vorticity will cause that point to rotate around its
No.
axis.
Vorticity is a deformation rotation effect. If you include the viscosity, yeah, that kind of thing happens, but this is obviously not that kind of thing happening. But it's a vortex flow, this kind of flow field. But each one of them just slide over without deforming, rotating,
Okay.
right? This is ideal vortex. Go ahead.
So when you say that each one slides over without rotating, are you saying it doesn't rotate with,
This thing slide over, just
Okay.
like this.
so it doesn't rotate with respect to the surface, but it still
With
rotates
respect to
with-
this line is a streamline, let's say.
Okay.
Okay, it's just a sliding. It's not rotating, deforming. Okay. All right. So that's called ideal vortex flow field. You are going to be given this in Unit B3. Okay. Wait until you see it, but we're going to analyze it later mathematically. Okay. So let's find out the circulation here. So this is the equation for circulation. You're probably dealing with it right now in Unit B1. Which equation do you want to choose? One of them is not varied. First one. So this one, you cannot do this because del cross B is 0. If so, circulation is negative integral over the closed surface S. Vorticity del cross B, we know this is 0. Dot product the area S, this is what? This is, answer is some kind of constant, indeterminate. The only thing we know is this is a constant. It could be 0, it could be non-zero, but we never know. Indeterminate integral. Okay. So we cannot use this equation. We can only use this line integral. So let's just do line integral. Okay. So first thing first, you don't want to deal with Cartesian coordinate. You want to convert this into polar coordinate. So this is a given velocity field. Velocity B is equal to ui plus bj. This is a Cartesian-based velocity is given. So you are going to completely transform into polar. So polar coordinate, velocity can be represented by what? Velocity in radial direction component and velocity in tangential direction component, right? You have to do complete transformation of coordinate. Do you know how to?
If you're working on a circle, X purpose was for
Well, there's a transformation equation coming from Unit B1. Do you guys know that? Please tell me that if you know. Okay, so velocity u is y over x squared plus y squared. Velocity b is equal to negative x over x squared plus y squared. Yeah, that's right. So what is the transformation equation?
This is a,
Oh,
u is equal to
u equal to?
sine theta over r. So it'd be r cosine, or r sine theta over r squared.
Where did you get that?
Isn't y equal to r sine theta? And
Okay.
polar coordinate?
So you get it from Unit B1? Which page? Somebody please tell me, unit B1, which page you got that kind of information at? Let's take a look at unit B1. Where did you get that? Somebody please tell me.
Page 2.
Page
that's
2.
some
Page
of
2,
it.
huh? Page 2.
For the grading this.
Here we go. Page 2.
Yep.
So this is from Cartesian coordinate to polar coordinate. You're going to go through a series of these equations, transformation equations. From polar coordinates to Cartesian coordinates, you have to go through a series of. Okay. So what you need to be doing is originally velocity is given in Cartesian. Velocity u is a function of x and y. And then velocity v is also a function of x and y. Then you want to completely transform into velocity vr. This is a function of r and theta. And direction er plus velocity v theta. This is a function of r and theta. In the direction is theta. That's what you want to know. Okay. So this is basically transformed equation of velocity field. This is originally given equation in xy Cartesian. Start from here, you arrive here. Let's do that. Okay, so this is again given in unit B1. Okay, I hope you're working on it. So let's go back to this note. Okay, so I'm going to apply. So x equal to looks like r cosine theta and y equal to r sine theta. X squared plus y squared is equal to r squared. Okay? So starting from here, u is equal to y is r sine theta. X plus y squared is r squared. You can cancel one of the r here. So this r and this r cancels. Okay? So what? U is equal to sine theta over r. And b is equal to minus x over x equal to r cosine theta. Okay. So b equal to minus x, x equal to r cosine theta. Divided by x squared plus y squared is r squared. Okay, so one of the r cancels. This and that cancels. Then this is going to be negative cosine theta over r. Okay, so far. This is not done yet, because what we want is velocity vr. Velocity vr. Velocity vr is u cosine theta plus b sine theta, which is equal to u is now sine theta over r, right? Multiplied by cosine theta plus b is now minus cosine theta over r multiplied by sine theta. So this is going to be what? What's this? What is BR? What's BR? This is actually zero. It cancels everything. So there's no velocity in radial direction component. That's what kind of flow field it is. So velocity in the radial direction component is zero. What kind of flow field? This kind of flow field. Velocity is always this way, not this way. It's called vortex flow. Okay, you can tell now by looking at it. So, okay, so far? Making sense? Okay, so b theta. So now what's b theta? B theta is minus u sine theta plus b cosine theta. Okay, so this is minus u is sine theta over r multiplied by sine theta. Looks like sine squared theta comes in. Plus b is again minus cosine theta over r cosine theta. What's that? So it looks like this is sine squared theta cosine squared.
Looks like R.
Negative 1 over r. Huh, okay. Very simple. Note sine squared theta, of course you know, sine squared theta plus cosine squared theta is 1, of course. Okay. So you got that. So what is the velocity field now? Velocity field is BRER plus B theta E theta, which is BR is 0, B theta is 1 over minus 1 over R E theta. So this is the velocity field you got in polar coordinate. So now you completely transform the velocity field from Cartesian to polar. Ready to go. So ready to integrate. So next thing is circulation. Let's find out circulation. Circulation is given by circulation gamma is minus integral over closed loop path C B dot the S is a line vector. Whoa. Go ahead,
Can
question.
we replace ds with r d theta?
That's right. So let's just take a look at that detail. Okay. So that's a great point, Peter. And then make sure everybody understand what you just said. Okay, good.
Structures.
Well, or otherwise, you are the only person know about. Okay, anyways. So you want to integrate over this closed loop path C. Okay. So this is a closed loop path C. Okay. Right. In terms of theta, this is the theta equal to 0, theta equal to 2 pi. Now we are talking about polar coordinate system. This is the direction r, this is the direction theta, okay? Theta equal to 0 all the way to 2 pi over the radius r. So along this path, let me just zoom in a little bit. Zoom in a little bit. So you are going to introduce very small, tiny angle d theta. Okay, this is d theta. And this is something called ds. By the way, ds is a vector, isn't it? What kind of vector is that? Line vector ds. What kind of vector is this? This is the direction tangent at each location. The magnitude is ds, which is arc length. So what is this arc length, by the way? ds is equal to
r d theta.
r d theta. That's right. So that's what Peter was talking about. Okay. So this is the line vector magnitude is r d theta, direction tangent at each location. So knowingly, you're going to integrate. Here we go. So this equation can be represented by negative integral from theta equal to 0 to theta equal to 2 pi. Okay, 5 more minutes.
Okay.
Velocity is this, right? Velocity is minus 1 over r e theta. That's the velocity. Take a dot product. You guys know dot product. What is ds? We just found. What's the ds?
r d theta.
r d theta. What's the direction? E theta. Right? So this is velocity v. This is ds. Right? This is velocity v. This is ds. Right?
It's just 2 pi.
So take a dot product. And then finish up in 3. What do you have?
2 pi.
2 pi. Okay, so this is going to be negative. Integral from 0 to 2 pi. If you take a dot product, what happens? Well, you just take the magnitude. Minus 1 over r multiplied by r is 1. And the minus minus. So this is d theta. Actually plus. Yeah. So, yeah. Minus goes away also. So this is integral from 0 to 2 pi d theta. What is it? This is 2 pi. In terms of unit, this is going to be feet square per second. So this is called the circulation of this flow field. Okay? So you can mathematically determine and calculate circulation of a flow field if velocity information is given to you to describe the flow field. So this is something the software X5 actually does. Okay? So you're going to actually start using that software toward the end of the semester. So next class, as we come back on Friday, we're going to start talking about two important mathematical functions. One is called stream function phi. Okay? This is Rome against Greek. Am I correct?
Yeah.
Phi. Rome against Greek. Okay. The other one is, sorry, stream function psi.
Yes, psi.
Psi. So, stream function psi. Is this correct?
People call it psi or psi.
Psi or psi. And the other one is velocity potential. This is phi. So some of you actually use this to represent 0. You have a habit of using this to represent 0. I'm talking about you, Heidi.
No.
Let's stop it.
Okay.
Okay, because from now on, I'm going to take it as a phi, not a 0.
Okay.
Okay? Sorry about that, but we have to stop it. Anyways, let's stop here today. And see you guys back on Friday.
Yeah, it's based on the expansion, but like what you're doing is you're taking a small angle over the entire angle. So it's still you're taking small angles, so it's down. So it's okay.
Do you have any questions? All right. Have a good day.
Hey, Peter, for dynamics homework,
Yeah.
is it the same number as the ones in the back of the book?
Which problem? First one was like 18.
It's super easy, but
Yeah.
I'm getting the wrong
It's like
answer.
18 point something. For-
Okay, yeah, you go with a lot of them, so I did something stupid. I got the first one right, that one was super easy, I just couldn't get the second one, so I gotta go back and finish it.
I sometimes.
Yeah, no, they're simple problems, I don't know what the fuck this is. I got that one right, and it didn't take me that long.
But if it's an open,
I was
You can also do it with open
Okay, so for problem one, did you account for the fact that the block wouldn't actually move for the first like little bit of time because the
cross section of the circle that they're integrating over DS.
Yeah.
And so anybody who saw that had extreme pain yesterday because it was a horrible problem.
Yeah, I was gonna say,
Yeah,
wasn't that
integrate this way, that.
Yeah, exactly.
wasn't that literally problem one on our homework?
That was problem 1 through
Three.
1, 2,
One and two.
3
Part of
times.
three.
Oh, that's
3 was half a circle, so yes.
With 2 segments on the end.
That was easy.
You just chunk off the segment.
Oh yeah.
It's a finite element.
Oh yeah, that's what we were doing. It's just like, hey, I know that problem.
Yep.
Finite element.